and they come from food, right? The food we eat or electrons stuck onto carbon backbones, right? So, and the carbon backbones comes from CO2 and the air that plants come to bring together, and then the electrons, when the water molecule is broken in plants during photosynthesis using sunlight, right? That's where it kind of all starts. And then plants stick electrons onto carbon backbones, and then they make hydrocarbons, and then those we end up eating. So the whole point of metabolism is to take electrons one by one, pick them out of the carbon backbone, the carbohydrates, the lipids or the proteins that we eat, and then those electrons want to flow kind of ultimately to oxygen. So oxygen is the final electron acceptor. So in the battery electrical circuit analogy, the oxygen is the positive pole on the battery. So the electrons want to flow from food to oxygen, and from this carbon-based molecule to oxygen. And if you do this at kind of room temperature or at the high temperature, I guess, but in the dry environment of air, that's fire. If you have electrons jumping on oxygen, this is like really exothermic, right? It's combustion. So if you heat up a piece of paper, right, to hot enough, then the electrons that are stuck on the paper are going to jump onto oxygen that's in the air, and that's going to make a spark, and it's going to kind of produce a puff of heat that's hot enough to then create a chain reaction. Richard Feynman had this beautiful explanation of what a fire is, which is basically this chain reaction of electrons jumping on oxygen and then releasing energy and then kind of creating more of this. So this is exactly what happens when you start a fire, but it's also exactly what happens, electrons jumping on oxygen in your body. But you don't combust because in part you're wet, right? The body is like a big percentage of water, about 70% water. And metabolism kind of breaks down this process of electrons from on carbon jumping on oxygen. Instead of doing it in one step that releases a big puff of heat, it breaks it down into hundreds of reactions, which we call metabolic reactions. So it slows down, right, the combustion, so that you're burning a little hot. Like, the reason we're warm is because of this heat released with the electrons flowing through each little resistances. So the insight of the energy resistance principle rests on this, that there's electrons from food that want to get to oxygen and this metabolic circuitry. And then as the electrons flow from food to oxygen, they meet little resistances. And every time electrons meet a resistance, an enzyme or some other component element in the system, there's an opportunity for transformation, right? There can be no transformation without resistance.
Yeah. So if we use a even more mechanical analogy, if everyone's probably seen like a stream of water, and the water can flow into a wheel or a turbine or something, and it will, as it goes downhill, it can turn something, and you can hook that up to something else that will do work for you. Move something from one location to another. You need that flow of stuff because it's going to have energy with it to do work, to move something from point A to point B or whatever. And what you're saying is basically, we're talking about literally electricity, like the same way that I have electrons in the wires of my home that give me my lights and my computers and everything. There's electrons that come from our food, and they want to flow to oxygen because that's just how the periodic table works. So we breathe in the oxygen, we take in the food, the electrons just